session.
Thank you, Angelika. Um, my name is Eddie Bon. I'm from Astronomical Observatory in Belgrade. And I will now present you Dusan Keres. The title is Galaxy Evolution with Stellar Feedback and Cosmic Rays. Dusan, you can...
Yeah, I was muted, sorry. Yeah, thanks, Adi, and big thanks to organizers for inviting me. It's a pleasure to do this, even though it's remote. It would be much even nicer in person, but thanks so much. So I'll talk about galaxy evolution mostly from the perspective of cosmological simulations, and then I'll, after discussing stellar feedback, I'll also discuss potential consequences of including GeV type of cosmic rays in these simulations. So this is the work done in FIRE collaboration, and lots of stuff I'm going to be presenting was done by my grad student TK Chen, but there's a big help from everyone else in the collaboration. All right, so first thing that puzzled me when I started doing this galaxy formation is what's going on with the universe as a function of time. Why is the universe forming stars over basically the old times we can see? There's only like first few 100 million years when we don't see it, but then for the past 13 point something billion years, star formation keeps going. So this plot here shows so-called Madal plot, sort of star formation rate density per unit volume of the universe. And you see that star formation activity peaked somewhere around redshift of 2, but it was still active at redshift 5, and it's still active today at redshift 0. And in fact, there is a huge range of cosmic time between redshift of 2 and 0, so most of the stars actually form in this semi-declining part of the star formation activity. And in this time, galaxies change significantly. So they used to be very chaotic and kind of crazy looking, like the ones on the upper right. And today, typical L-star galaxies that we observe are nice, smooth, star-forming looking disks. They're also the ones that stop forming stars, but the ones that do it very differently than in early times. So the question I would like to answer is what happened with star formation activity? Why is it changing from much more rapid to slower? And what happened to galaxy? Why they're so much calmer than they used to be? And how is all this connected to what's going on with the gas at the intergalactic medium? So for a while, I personally, but also the field, focus on like what drives the growth of galaxies. And in cosmological simulations, we found that especially at high redshift, galaxies are mostly growing through the by eating of this cold filamentary inflowing gas that comes very close to galactic vicinity. And this gas doesn't have to wait for a long cooling time in virialized atmospheres. Its cooling times are short, and it can go basically to the center of halos. So because the structure grows very fast at early times, then almost all of this growth of structure ends up somewhere close to galaxies, and they can have pretty high star formation rates. So at late times, things change. So by redshift of 1 or even 0, typical L-star galaxies are believed to be surrounded by hot halos with more diffuse atmosphere that have to wait for some cooling, and the structure in general grows slower. So the supply rate to these galaxies drops. So we think that the main reason why galaxies are forming stars so fast at early time is the growth of structure and efficient mode of their feeding, and at late times it's slowed down in both of these processes. But when you ask yourself, okay, is the info all of the stuff we need? The answer is no. Info is only a small part of the story. So if the growth of galaxies is not regulated, they simply form too many stars and end up too massive just by these infalling processes, whether they're slow or fast. And this was pointed out a long time ago, and it's illustrated on the figure on the left. So the black line shows the observed stellar mass function of galaxies, so number of galaxies per unit volume. The red line shows the results from typical simulations at that time that had only gas cooling and infall and structure formation and UV background, but no feedback from within the galaxies themselves. And you can see also a third line that is a thick black line that was just done by hand by me. It's an approximate line that would show what would be the stellar mass function if all the baryons in galactic halos ended up in stars. So galaxy formation, this simplified simulation is very efficient. It's not that far from everything cooling into stars, but it's far from the observed galaxy mass function. The differences are especially huge at low and high mass end. And the way you should look at these functions, you should try to match number density of massive objects versus number density of low mass objects. So at massive end, there is for the same number density, there's about factor of 3 or so higher masses if you don't have efficient prevention of galaxy formation. And at low masses, this factor can be 10 or even 100 if you try to match the same number density. So something has to regulate this, and currently prevailing thinking is that at low masses, below L star or around L star, it's mostly stellar feedback, where momentum and energy gets input from young massive stars. And at high masses, it's mostly being associated with AGN feedback. So in this talk, I will leave the high mass galaxies aside and focus on L star and lower, where stars might be the rulers. All right, so how does the stellar feedback affect galaxies? Well, we see galactic outflows at all times. So large-scale outflows going to kiloparsecs, sometimes even tens of kiloparsec scales, are seen in star-forming galaxies. They're common at high redshift. So whenever you stack any kind of population, any kind of population of galaxies and trying to find their absorption spectrum, absorption lines from variety of ions are blue shifted, indicating that something in front of this galaxy is going towards us. So an example here is from Silicon-2, but you can take other species as well. So regardless of the population, high redshift galaxies are just spewing out lots of gas. At late times, close to present time, this is much more rare, and you typically need rare starburst galaxies to see it, but there are examples like this M82 galaxy where you see both hot gas ejected, also cold gas ejected, and even partially dust being ejected from these galaxies. And one would like to include this kind of stuff in cosmological simulations that we use to study infall, but that's difficult because we want to know how much material gets ejected to hundreds of kiloparsec scales, and we need to start from the parsec scales where stars are actually forming and imprinting their energy. So oftentimes this leads to a simplified prescription. We just say, okay, this galaxy is going to eject this much material. We don't care what happens. But in the last 5-6 years, there is big progress on trying to model things self-consistently from smaller scales, from roughly parsec or tens of parsec scale all the way out to megaparsecs. So an example, this kind of model is the collaboration that I work in, and I'm one of the PIs. It's called FIRE collaboration. So that stands for Feedback in Realistic Environments. And in order to capture what's going on in these smaller scales in galaxies, we need pretty high resolution. So in dwarf galaxies, we go down to tens of solar masses per particle. In the largest galaxies we model, it can go all the way to 10,000. And the resolution can be even sub-parsec in dense regions. And in the poorest cases within the ISM, it's typically tens of parsecs. And this is crucial, and it wasn't possible before we had more powerful computer, because high resolution and detailed cooling processes in the interstellar medium enable you to get concentrated clumping of giant molecular clouds, and within those clouds, concentrated formation of stars that then undergo supernovae at almost the same time and almost the same location. So this time and spatial coherence of where you put in the energy is important for what comes next. So once we form a lot of stars in these models, they input ionization to the surrounding region. They form H2 regions. They have stellar winds. They have photoelectric heating, radiation pressure. And most importantly, young stars explode a supernovae, and they input energy and momentum to the surrounding. So what was the issue with previous model is that when supernova explodes, it first hits the surrounding gas, and then the Sedol-Taylor field will expand it, and then pushes by momentum. So if you have low resolution and explode the supernovae, then they actually cool before this bubble can expand and push the surrounding gas. So for fire, we came up with a model that basically uses sub-resolution information, even at those parsec or 10 parsec scales, to figure out how much momentum you should put to the surrounding material in a resolution insensitive way. And that's actually key for this fire feedback to be successful in kind of driving the galaxy formation and injecting material. And unlike some models, we also always include hydrodynamics and cooling, because sometimes if you turn those off, you can have more efficient ejection of material from galaxies. So the movie that I'll just play again, it's just showing an example from these simulations where lots of tiny proto-galaxies are forming at early times. The movie shows gas color-coded by temperature. So green is roughly 10,000 degrees, red is roughly 500 to million degrees, 500,000 to million degrees, and magenta is like 1,000-degree gas. So lots of these tiny galaxies form, and at early times, they're forming stars in a concentrated manner and manage to have these episodes of ejection of material and then kind of reaccretion of that material. But by late times, the star formation is spread throughout the disk, and as we mentioned, the feeding is lower. So these concentration ejections are not happening, and even if they do, they're not able to eject material very far from these deeper potential wells. So in these simulations, we actually have this interesting switch between super efficient ejections and almost not happening at all. I'm just gonna stop the movie and proceed. So the outcome of the simulation is that now the stellar masses of these galaxies are actually in much better agreement with what observed. So this is the stellar mass, halo mass relation, and these different solid and dashed lines are observational estimates, and different symbols come from our early simulations. And the good thing about this is that agreement is actually very good, and it just comes from the input from stellar population synthesis model and assume initial mass function. We didn't tune exactly what's going on in small scales and how much we should eject it. All the ejection part comes naturally for this much energy input. This is what you get in galaxy formation. And some of these galaxies look pretty, but you'll see later on that that's not all that we should look at. Pretty doesn't mean physically good. So let's see what actually happened with these galaxies and how did they form the way it's seen in the movie. So at early times, when galaxies are small, they typically have this concentrated central starburst, and that drives bursts of star formation, that drives burst of feedback, that drives burst of outflow, and then it like semi-shut itself because it ejected too much gas. So it has an episode of much more quieter growth until either this material comes back or filaments reconnect and feed the galaxy again. So in this figure done by my postdoc Sasha Muratovi, show star formation in black. This is actually multiplied by a factor of 10 compared to other lines. And then ejection of material outward in red and infall in blue. So infall is semi-continuous, but the outflow is very concentrated in this strong burst. And you eject large amount of material, so mass loading is high. And then some of this material crosses quarter of the virial radius, which is dashed line, and some of it is even injected into the IGM, which is this dotted line. All right, so when we measure how much material is ejected, that's typically done by using something called mass loading. It's just a ratio of the outflow rate to star formation rate measured over long time scales. We find that in dwarf galaxies, we can eject 100 times more than it ends up in stars. And in massive galaxies, this drops to close to 1. And then in Milky Way-like galaxies at late times, which are shown by these arrows showing the upper limit, it actually drops to close to 0. And this is illustrated in this plot. So now this is the late time star-forming galaxy. star formation is not bursty anymore. It's much more continuous, and the outflows are almost dead. I mean, there is some material that keeps going in and out, but it's a very, very small fraction. So there is an inflow that drives star formation, and that's basically it. So one can say, okay, this is great, everything works fine, but it turns out that we didn't include all the physics that we think was relevant. And also, as we improve the simulation, some minor issues start popping up here and there. So we had good agreement with structural properties of galaxies, mass metallicity relation, and then we wanted to see if adding extra physics can change something. So we added metal diffusion in these simulations. We added magnetohydrodynamics, viscosity, and conduction. And these did not really affect galaxy formation in a significant way. The movie that I showed you would basically look the same. The difference is that a little bit of more gas managed to cool on the galaxies, and stellar mass halo mass relation became a little bit higher than observation at redshift 0. There was potential that maybe this is governed by AGN because we're going to L-star galaxies, but we also knew that one important component of interstellar medium was missing, and that's cosmic rays. We know that cosmic rays are produced in strong shocks, and you heard a couple of talks about them in this conference. And they, most of the energy density of cosmic ray in the ISM is most likely produced on supernova shocks. They carry about 10% supernova mechanical energy and can be important contributors to interstellar medium pressure. So we wanted to see how did these things potentially change galaxy formation and what's going on with them. So with TK Chen, my student, and Phil Hopkins and a couple of other collaborators, we set out to explore this in a long-term fashion. And we first worked on numerical algorithms, how to do it. We came up with this two-moment transport scheme that it's not important here, but the point is we can test variety of diffusion scenarios of cosmic rays through galaxies pretty quickly. So that helps us. And what we do, we have still the same fire feedback, but 10% of mechanical energy that would go into this Sedow-Taylor phase, or at the end of Sedow-Taylor phase, we just say, okay, this fraction goes to cosmic rays, the rest will do its standard work. And then we wanted to see how these cosmic rays propagate through galaxy, and they usually do it by streaming and diffusion processes. And I just want to point out here, we really only care about few hundred MeV to few GeV cosmic rays that have bulk of energy density with the ISM. This might not apply to very, very high energies. So we tested variety of diffusion scenarios. We had isotropic and anisotropic diffusion, different streaming speed, and so on. And we found that outcome for galaxies, it's actually very, very different depending what you do with cosmic rays. So you can actually first focus on the top three panels in this figure here, and they show just how the cosmic rays end up being distributed after a couple of billion years of the evolution with three different diffusion coefficients. So this would be 3 times 10 to the 27, 3 times 10 to the 28, and 3 times 10 to the 29. And this diffusion coefficient basically regulate how fast cosmic rays move through the interstellar medium and through the intergalactic medium at the end. So for slow diffusion, lots of them stay confined to the interstellar medium. That's because they have huge hadronic and Coulomb losses. They just lose their energy and they are not able to leave. For higher and higher diffusion, they can leave further and further out from galaxies and have lower and lower losses. And for the highest diffusion, you see that they start affecting the surrounding gas into this kind of outflowing structure far from the galaxies. So which of these is correct? I mean, these were all reasonable coefficients when we started, and we wanted to constrain them. And one way to constrain them is by using diffuse gamma ray emission from galaxies. So cosmic rays move through the interstellar medium and they interact with nuclei and produce neutral pions. These neutral pions decay into gamma rays. So we can measure gamma rays as like a measure of how much of these interactions you had in the ISM. And it turns out that if all of the energy is lost in these interactions from the cosmic rays, you have this dashed line here, which is like a colorimetric limit. All of the energy is sucked out and radiated indirectly through gamma rays. So there is a mess in this diagram, but just pay attention to different colors for these 3 diffusion coefficients. They're color coded differently. And you see that in order to match observations that are shown with these empty symbols, we have to have the highest diffusion coefficient we have tested. So this is especially constraining for, I think one of these is M31, the other one is, the other 2 are Magellanic Clouds, and even Milky Way. They have actually pretty low gamma ray emission compared to colorimetric limit. So from this, we concluded that diffusion coefficients of 1 to few times 10 to 29 centimeters square per second in an effective sense, so this is effective transport through the galaxy, are needed to explain the gamma ray observables. So what is the consequence of these kind of cosmic rays? Well, first of all, for dwarf galaxies, there were almost no consequences. So this on the left, the plot on the left shows what happens when you have simulations without cosmic rays, which is this red Hydra symbol and this pentagon MHD symbol, and then with cosmic rays with 2 different diffusion coefficients, which are axes and circles. So you see that at low masses, 10 to 10, 10 to 11 solar masses halos, there is no difference. But once you get to Milky Way mass halos, 10 to the 12, there is some systematic difference where simulations with high diffusion coefficients that we prefer from the gamma rays ends up being less massive than the ones without them. And the reason for that is that, shown on the right, the late time star formation is suppressed in these kind of runs. So at early times, they're similar to what we have with normal feedback, but at late times, for some reason, they're forming less stars. So we wanted to push and see what's going on there. And the bulk of the difference is actually shown in these semi-complicated plots. So on the left are simulations without cosmic rays. On the right are with cosmic rays. And different lines show effective pressure, or basically just energy density that's kind of needed to balance the gravitational pull inward. So the black line is what you need from gravity, and the rest of the lines are kind of contribution from different components. So on the left, in the inner 10 kiloparsecs, and same on the right, you see that everything is supported kinetically. That just means that these galaxies rotate. If they don't rotate, they would collapse. Going about 10 or 15 kpc, on the left, most of the support comes from the thermal component. Those are hot virialized halo. And on the right, most of the support comes from the cosmic rays. And the thermal component is actually suppressed by almost an order of magnitude. It turns out that these cosmic rays directly and indirectly suppress some of the shock heating of the gas, and also are able to hold the whole halo intact, basically just this non-thermal pressure that holds gas from collapsing. They're also able to drive weak winds far away from galaxies, sometimes even to megaparsec scales. And all of those processes combined manage to suppress late-time star formation and lower the galaxy mass. So as a semi-final point, I just wanted to show something interesting that is important when we try to interpret different phase structure of the gas around galaxies. And that's the role of thermal versus non-thermal pressure. So on the upper panel, I show different phases of the gas surrounding the Milky Way mass halos. So 10 to the 4 degrees gas to 10 to the 6 degrees gas. And you can see their typical density as a function of galactocentric radius. So the cold gas is always very dense, and hot gas is always low density. So they're in pressure balance. Cold gas is confined by the hot gas, and it's in these dense clumps. But once you have cosmic rays dominating the halo, then the non-thermal pressure is the most important thing that exists. And the thermal pressure is not that important anymore. So you can have all these phases sitting roughly at the same density and still be in pressure balance because there's this non-thermal pressure support. And that has big consequences because some of the diffuse absorbers that people find around galaxies and some of the low temperature gas that's so common around galaxies might actually be caused by the fact that there is this non-thermal pressure that allows to have diffuse cold gas all around. And so this is my final color plot that shows the temperature density diagram in MHD simulations without cosmic rays and with cosmic rays. And the typical temperature in these halos drop from around 1,000,000 degrees to only about 100,000 degrees because of this extra cosmic ray pressure that prevents shock heating of the gas and also ejects some of the warm gas from galaxies and enables cold phase that exists to be spread out such that the overall cooling of the whole halo is just much more efficient. All right, so I took out slides that talk about detail ions here, but if you're interested, I can show them later. So I'm just gonna summarize the story here. So strong outflows pollute circugalactic medium. They're prominent in low mass galaxies and are much weaker in late times in thin disks. So this is true both observationally and in these cell consistent models that can produce outflow now in the last 5, 6, 7 years. Cosmic rays are a potentially important ingredient in galaxy formation. They have to escape from galaxies pretty fast if you want to match gamma rays. And if they do, and if the transport is as simple as we assume, which is probably not, but this is kind of the optimistic scenario, these escaped cosmic rays can provide non-thermal support that drives winds from these halos and slows down the inflow of the gas. Details are uncertain, but I think it's something we should keep exploring because they can change the outcome for Milky Way mass galaxies. So thank you.
Thank you, Dusan. Now, I mean, this is really interesting things, really interesting simulations that you were doing, and I think that probably there will be some questions. So we are now open for questions. Just unmute yourself and ask questions if you like.
Hey, Miroslav here. So I would imagine that the missing satellite problem in the Milky Way, missing satellites problem in the Milky Way is not a problem anymore. This pretty much explains it, right?
So the stellar feedback pretty much explains it. This is a little bit different from what I talked because the cosmic rays don't affect it, but stellar feedback affects it really strongly. And there is another twist to the satellite problem, and that's the fact that the massive disk of the Milky Way-like galaxy also destroys some of the satellite through tidal processes. So if you run dark matter-only simulations, you have too many low-mass objects, seemingly. Some of them are destroyed, and some of them will have super inefficient star formation.
Nice.
I sad treba da se pojavite, da se...
Milane,
just a moment, please. Moderators, could you mute any of attendees, please, who are unmuted now? Thank you.
I apologize, Dusan. You can continue. So if there are some more questions, or you wanted to continue.
No, that's basically it. I mean, the satellite statistics are in good agreement now. There are issues now with like some ultra compact satellites and stuff like that, but in terms of statistics, it works out.
Okay.
Can I have a question?
Yes, you can.
Okay, thank you, Dusan, for a nice talk. I just wanted to comment that there are recent papers that the cosmic rays actually influence more the evolution of the supernova remnants than we believed previously. And for example, Dissing and Caprioli in 2019 published a paper which stated that maybe this influence on the galaxy formation may be two or three times larger than we expected because of the different dependence of the adiabatic index of cosmic rays with respect to the ordinary gas. So this is something new based on the works of the Bell. which stated that there are actually cosmic rays that escape the remnants and those that are inside the remnants and that are released at the end of the evolution. So their importance should be taken more seriously. Yes.
No, I think it's a good comment. So when we do this sub-resolution model of how much momentum you get in the Sedow-Taylor phase, we don't explicitly account for cosmic rays in there. So we just let them then move through the galaxy and do this kind of secondary damage or provide pressure gradient. So it's something we should look at more.
Yeah. Okay, thank you.
Thanks.
If there are... Yes, sorry. Diana, yes. You can ask a question if you already started.
Okay. No. So my question is of the new model and the calculation. So did you look at the outflow that is only driven by signal explosions or outflow because they saw a lot of sort of mergers there? Did you also do the merger-driven outflow tidal interactions or something like that?
Okay, so I'm not sure if I heard your question fully, but I heard something about outflow and mergers and tidal interactions. So I'll try to answer bits and pieces, and maybe you can ask questions or type in a chat or something if this is fully off. So outflow here at early times, we just state that they are driven by small-scale local starbursts because they are very frequent interactions between galaxies at the time. It's possible that some of this is indirectly driven by interactions. The actual outflow would happen anyway if you have central starburst, but it's possible that some of the cycle might be starting when you have the first interaction, and then once you start ejecting gas and recycling, it probably go through a couple of cycles on its own. But the actual mergers of galaxies are not crucial to produce these strong outflows. So interactions might be more common than we might naively think, but the mergers are definitely not super common. And I don't know if I was this.
Well, it's sort of related because the reason I'm asking because something that's been looking into recently is nuclear acceleration in tidal interactions between galaxies, merger shocks, and so on.
Diana, I have to stop you because we cannot hear you well. Practically, it's you can continue because we already passed the time. Now it's 6:02. So if you like, you can continue on chat on these questions, and we have to continue with someone that follows next, and that is Gabriela Zacharias, and the title is Stereo Electrovolt Dark Matter Search Program with the Cherenkov Telescope Array. The strategy and synergies with current gamma ray experiments. So please, Gabriela, you can now continue.
Okay, thank you. Do you hear me well?
Yes.
Okay, good. Thank you. Right, so this talk will be a bit less, I was first worried that is less cosmology than other talks in the session, but in fact, as Dusan, introduced the relevance of cosmic rays and answering the cosmological questions, I think this fits very well in. So I would be talking here about how we can use cosmic rays, in particular gamma rays, to hopefully to say something about the nature of dark matter particles. Oops, sorry. So first thing that I wanted to mention is that in terms of, so of course, as we've seen in this section abundantly, dark matter is the dominant component of the universe. However, of course, we do not know what it is made of and if it is made of particles at all, but here we will assume it's made of particles. Further still, if you continue making assumption, one of the motivated ones is to assume the dark matter is thermal, as it is usually said, which means that in particular, we can make an assumption. The dark matter particles were in thermal equilibrium early on in the universe, and then they decoupled due to expansion of the universe at some point. And so basically whatever amount of dark matter particles we have today is a consequence of this thermal decoupling early on. And so this is a simple assumption. It's very, actually turned out to be quite reasonable from many viewpoints. And so these models, in fact, very well studied and actually tested, as I will show later. But the main point for this thermal dark matter is basically this fact that if we test this way the dark matter particles annihilate with each other, we basically can say something also about what was happening to them in the early universe. And these models are also motivated from particle physics because they assume new physics at around Z boson mass scale. So they fit very well in this LHC program and so on. And so basically these thermal dark matter models often are called also WIMPs, weakly interacting massive particles. And as I said, they're very well tested over the past decades. You have LHC that tests them. You have direct detection experiment, which tests, which sort of try to measure how nuclei in detectors could recoil if they're hit by dark matter particles, dark matter as Earth passes through the dark matter halo of our galaxy. And you have these indirect searches where you basically, again, as I was saying, look at annihilation of dark matter particles into some standard model particles, meaning cosmic rays, and try to catch them this way. And so what we see here is that basically these are constrained. This is the mass of would be dark matter particles. So here is it's say 100 GeV and TeV range somewhere here, and here is a cross section. And so you see that all these different searches basically constrain a lot of this parameter space. Okay. However, if you want to combine, basically combine these searches, you have to assume something about this sort of bubble in the middle. So these constraints are always model dependent. But another thing is that even though we are sort of losing hope on these sort of models because they have not been found yet, despite all these huge and expensive instruments, there is still, I mean, they're not basically tested enough to make any sort of conclusion. In particular, this TeV mass range is not yet explored. Okay, and this is something that I will talk about here. Just a little bit more by means of introduction. So basically, oh sorry, basically to make clear what it is that we are trying to find here is, as I was saying before, as two dark matter particles annihilate, they produce in astrophysical objects today, they produce all sorts of, cosmic rays. And we are interested in looking at stable ones. In particular, you will see gamma rays, and also at the energies of GeVs or TeVs or so. So gamma rays are quite powerful astrophysical messenger because they travel in straight lines, so you can see the morphology of your emission region, and they're more abundant in neutrinos. And so, of course, gamma ray astronomy is a huge, field developing over, last many decades. You can measure gamma rays from satellites or from the ground. In particular, what we are curious about here is basically that so far we did develop both techniques very well. So if you look for satellites, for example, there is a Fermi-LAT satellite and Agile that were both launched, say 11, 12 years ago, and cover lower energies. So here again is a TeV. So here is hundreds of GeV. So they cover hundreds of GeV gamma rays. And so we have lots of results with those I might mention later. And then we have ground-based telescopes that cover above TeV or so. And again, those are telescopes that we had from the 70s. They're very complementary with each other. Aside from these different energies that they cover, their difference, so I'm sorry, let me just try to see. my own slides better. So the main difference between the two of them comes from the fact that satellites are above the atmosphere, okay, and they measure gamma rays directly. So for every event that we see in the detector, they're like particle physics detectors in space. So for every gamma ray that enters the detector, we know it is a gamma ray. So we have exactly gamma ray maps. However, from the ground, we observe showers. So whatever cosmic ray hits the atmosphere, we just see the shower on the ground. And for every gamma ray that hits the atmosphere, we have 10,000 protons or so. So these telescopes, for them, it's harder basically to say which event they see is a gamma ray, which one is not. So they have these huge cosmic ray backgrounds. So this seems rather technical, but will be relevant for what I'm about to tell you. This difference is basically, sorry. Oh, sorry, it was just slow switching slides, I think. So this difference is basically determine also the kind of analysis you can do with this data, because with satellite experiments, basically you can do, you can build your templates, your models, different models that you think can fit your data. Then you put them through the likelihood analysis, and you see, how you best describe your data in terms of gamma ray emission. For ground-based telescopes, it is harder because, again, you have this proton background that it's not so easy to model. And so what they were doing, they were basically measuring. You have your region where you measure the signal, but then you measure the background elsewhere. And so it was quite a different approach. And this one had this approach for ground-based telescopes had a limitation that basically you could see only point sources and not extended emission. And so now, I'm sorry, I don't know why. Sorry guys, do you hear me well? It seems like my computer for some reason blocked.
Yes, we can hear you well. Just continue, please.
Yeah, it just doesn't let me change my slides. Yeah, let me see. Oh, wow. Yeah, sorry, it was blocked for a while. Sorry. Oh my God. Yeah, I don't know. Usually it's resilient, but might be that images are quite heavy. Okay, so anyway, so this picture sort of that I was mentioning before, ground-based in satellites. Now we are sort of entering the new sort of era in ground-based astronomy, because what is being built now is the so-called Cherenkov telescope array, which is an array of ground-based telescopes. But while before we had 4 at most at a given site, now it's an array of 70 or so telescopes. So it is going to be, this CTA is basically going to be something that sort of bridges between the satellites and ground-based, because, as I was saying before, Cherenkov telescopes usually observe just point sources, but because now you will suddenly have a large number of telescopes, you will do these surveys, you will observe large portions of the sky, and basically you can analyze the data and approach it more like a satellite experiment. And this is something basically that I will talk about here. So then if you want to use such experiment, basically to look for dark matter, how do you do that? So basically from dark matter, if you want to predict what is a gamma ray signal that dark matter particles say would give you, you need to know more or less how these 2 dark matter particles annihilate to gamma rays, say, meaning what is the spectrum that you expect. And this is something that you can do, it's particle physics, it's relatively well understood. On the other hand, you also need to know how your dark matter is distributed, that you get from n-body simulations that we heard a lot about in the previous talks. Though on very small scales that also we heard previously, we have lots of uncertainties. However, you put all these ingredients in, you have your model. And then you wonder, where should I look? Basically with my gamma ray telescope to hopefully find the signal of dark matter. And the answer is that one of the best places is the center of our galaxy. So what I show here is this dark matter halo of the Milky Way, where you see lots of subhalos. But then you see that in the center of our galaxy, you have lots of dark matter, and basically the signal. So here would be sort of, this would be sort of sun position around this in the spiral arms, but sort of the signal from dark matter in the galactic center is very bright, and it's also extended. And this builds to this that sort of traditionally it would be hard to see it with ground-based gamma ray telescopes, but CTA is sort of changing that. And so what I will talk to you about here is like how CTA now should look at the galactic center at TV, and if it will be able to sort of tell us anything about this sort of idea of thermal dark matter. So basically, galactic center is already in Fermi lat data is quite of a puzzling place. So in Fermi data, we see the whole galactic plane shines very brightly, but you do not see really galactic center as a special place. At TV, with Cherenkov telescopes, again, you cannot see this large-scale structure, but we know we measure tiny region around the galactic center, and we see there is some there. As I was saying, there are many open questions. Even though this star formation rate is huge in the galactic center, is not a special place in gamma rays. So the question is why. Then also, if you look better, you clean up your data, you see that in the center of our galaxy, there's such things as Fermi bubbles, huge structures that nobody, sort of predicted, even though it's probably related to AGN activity of our black hole. And then if you look closer still, closer to the Milky Way plane, you see some galactic center excess, some unexplained division. So again, not only for dark matter, but for many, many questions, this region is interested. There is some extended signal probably there that should be understood. So how is CTA going to approach it? So CTA is basically going to look as, again, given that it has lots of telescopes, it will not just observe the galactic center. So you see this is like 5 degrees around the galactic center. It will just it will not look just here, but so these are all fields of views of single observations. It will basically do this collage of observations, deep observation at the galactic center, but then it will go up to tens of degrees above. And so one can use now all this data to look what's, to sort of think how is the best to look and what one can find there. In terms of dark matter, again, one can build the models about the spectra and about the shape. So as I said, shape is quite uncertain, but one can play with two sort of limiting choices. One is being that dark matter could be very, very dense, very cuspy in the center. This is dark matter density, it could just fall very quickly outside of the galactic center. Another one model is that it could just be rather flat, its distribution. This will give distinct morphologies to the signal. Then one should include everything we know from the Fermi and other telescopes, like the point sources we know are there, and this emission from cosmic rays that we know are present in the galactic plane, in the galactic center from Fermi. So all these things, even though they were typically neglected by current ground-based telescopes because they're quite faint for them, suddenly become very relevant for CTA.
I'm sorry. 5 minutes just.
Yeah, thank you. I think I can do it. Another thing, aside from, including all these models that were not basically ever tested at these energies, one can also adopt the analysis techniques that were used for satellites. So one does not need to be limited anymore by this on-off analysis. This was traditionally used by ground-based, but can basically build models and use likelihoods to constrain using both informational morphology and on spectra of your models. But one can also do what is known that actually will be a problem is systematic uncertainty. In CTA, I will not bother you with that, but in this analysis we include also that, which is, again, was typically neglected previously. And so if one does all this, sort of tries to push the limit, I do not know if I mentioned, so CTA is in the construction phase, but it will become operational in 2 years, say, from now. At best, it will start becoming operational. So we still just have, predictions, what we can see, but this is all done to predict, what is the best we can do. so that we are ready when the data comes. So after all this game is played, we basically see that even if you include all the systematic uncertainty and you include all the interstellar emission that Fermi has observed, so all sorts of backgrounds that were typically not included, still CTA should be sensitive to this thermal dark matter. So basically here you see the mass, it's a TV, and here you see predictions for thermal models. So basically it seems that CTA will be quite good for this game. Another thing is that basically, so this is a bit technical slide, but the systematic uncertainty that we include here, we show here that it's not unreasonable, it's rather, it's quite generous actually. So this plot should be quite realistic. Another thing is that together with uncertainty of instrumental uncertainty, you do not know your interstellar emission very well, of course, also as Dusan was saying. And so one has to include also that uncertainty in the game. And basically we see that we need to know interstellar emission models up to like with 15–20% uncertainty if we are to test thermal dark matter, which is sort of optimistic, but it's not impossible. And the third point, the last point that I believe I'll make is that while previously, if dark matter profile, the density distribution of dark matter would have is chord, meaning very flat, that was a sort of a blind spot for ground-based telescopes because it would just look exactly like their cosmic ray backgrounds. So one would basically be not able to look for dark matter for this sort of distributions. So basically there was a danger that even though CTA is good for looking for, this thermal dark matter, if it's very flatly distributed, it cannot say anything. However, the point is that because CTA will look for in large region in the galactic center, up to 13 degrees or so, and we do not expect dark matter shape to be flat, beyond 10 degrees. So it would still be able to catch the change in morphology and still be able to constrain dark matter, thermal dark matter, even if it's cold. And so just the summary. So this is something I did not say before, but together with dark matter, so focus on dark matter, but basically our analysis shows that CTA should be sensitive to thermal dark matter, but also to the interstellar emission. Basically be able to map in detail how interstellar emission looks like in the galactic plane and in the galactic center. So this is very exciting and there are lots of physical consequences. We need to test thermal dark matter, we would need relatively good knowledge of interstellar models, but those would be mapped by the same telescope. So this is relatively optimistic, and we would be able to see dark matter even if it has a huge core. So basically, this is my last slide. Detection, of course, with CTA is not guaranteed. Dark matter can be anything. However, it's still a good bet to look for CTA, and who knows, maybe we'll get, pleasantly surprised, given that these models are rather motivated, and the CTA will actually have very good sensitivity. Okay, I stop here. Sorry, guys.
Okay, thank you, Gabriela. This was very interesting presentation. We have a time just for one quick question because we are a bit out of time. So if there is any questions, please unmute yourself and ask questions.
Hi. Hello.
Okay.
Can I ask a question?
Yes, please ask.
Thank you for your talk. And I wanted to ask whether CTA will
we
have...
cannot hear you.
Oh, I was hearing you, Anna.
Can you hear me now?
I do. I hear you.
Yeah, we hear you.
Better?
Yes, it's okay.
Okay. So hi, thank you for your talk. What I wanted to ask is whether CTA will have another target for looking for dark matter similarly to what was done with Andromeda. So whether the galactic center of Andromeda will be also one of the targets, or just what I saw was the large Magellanic Cloud. So will there be something done with Andromeda as well?
This is a good question. This is a good question. In fact, CTA will observe Andromeda as well, not with so many hours. And in fact, we were thinking, so now good that you mentioned, we might talk also offline. We were thinking with some student to just look, you know, what CTA will see there. Because it's less hours that is dedicated now, but if you can show that you can see something interesting, maybe we can push to get more hours. So, you know, if you're interested, let's talk offline.
Sure. Thanks.
Sure. Thanks.
Okay, thanks. Now then we can continue with the next talk. Milana Jovanovic, dynamical modeling of nearby galaxies. Please. We don't hear you, Milana. Milana.
Milena, could you unmute yourself?
Yes.
That, but once I go to this presentation screen, I lose the okay, now I think I'm unmuted. So I'm Milena from Astronomical Observatory of Belgrade, where I'm working on finishing my PhD thesis that is closely connected to dynamical modeling of nearby galaxies. So dynamical modeling entails observing the motions of test particles in a gravitational field of a galaxy. From these motions, we can then infer the total dynamical mass contributing to the gravity up to a certain enclosed radii. So furthermore, from this, we can get a detailed decomposition of the dynamical mass to the constituents, such as stars, gas, dark matter, and that is what we are presenting here. Mass is thought to be crucial for understanding the formation and evolution of galaxies. For example, it is thought to modulate the important processes in galaxy evolution, like star formation and quenching. How do we do this? As I said already, we observe the motions of test particles, and our test particle or tracer being the cold neutral hydrogen gas. So we are looking at the objects that are gas rich. We are also looking at the objects that are rotationally supported, contrary to the random motion supported objects. So it comes down to the disks of galaxies. Because for disks of galaxies, the virial theorem comes down to really simple expression like this, where we can connect the rotational velocity to total enclosed mass. Rotational velocity, on the other hand, for disks of galaxies translates to a circular velocity on a simple circular orbit inside of a disk. And for this type of objects, it's very well possible to get a detailed resolved rotation curve, which is a plot of rotational velocity with radii, and we're mostly interested in that. And all of this is done in a framework of Newtonian Einstein gravity, Newtonian being the important part here. So what we use the publicly available THINGS survey sample done with the VLA telescope. It mainly concerned with very nearby galaxies, so closer than 15 megaparsecs, but also the distances are larger than 2 megaparsecs that I didn't put in here, and the local group members were excluded due to the large angular size on the sky. Despite being a very modest size sample, it had a large range of masses, morphologies, and sizes included. Obviously, it was not complete. It was H1 selected. So early type galaxies, lenticulars, were excluded. So at 34 galaxies were in this sample, but only up to 20 were usable for this kind of analysis. As I mentioned before, the main part of kinetic energy should be in rotation. So this is taking some of the galaxies out of the sample. Some of the galaxies are undergoing interactions, and also geometry has to be favorable. So inclination is very important. 45 to 70 degrees is the most optimal. So the typical product from radio observation is a radio data cube, which consists of a series of snapshots of galaxy done at around the redshifted frequency of H1 line. So it was meant to sample the H1 line to get something like this in an ideal scenario. Usually we do not get something like this, but never mind. And from this snapshot, we take every pixel, every point on this image is across all the snapshots. Is supposed to give us a typical rotational velocity of that part of the disk. And when we acquire all these rotational velocities, we construct something that is called the velocity field, which is very, very important for further derivation of a rotation curve. So typically we had to fit or analyze like 1 to 4 million line profiles to assemble one velocity field. And it can be constructed in various ways. We used H3 Gauss-Hermit polynomial to fit because it deals well with the symmetries that are normally seen in radio observations, and a lot of other things. But in some cases, this was not enough. So we had to develop our own procedure to when some other parts, some other types of motion were present, then we have like a double peak or a blended line, and then we were supposed to distinguish a rotation from this other motion and construct a velocity field from that. This is one example of a very well-defined velocity field. The brighter parts, you can see that it has some holes, but this is a good one, trust me. So the brighter parts are representing the receding part of the galaxy, and the darker, the approaching part. And here I'm going to give you one rotation curve derived with different velocity fields, just to get you to have a grasp on how important the velocity field is for deriving the rotation curve. So this is a very special case of a very diffuse low surface brightness galaxy. Not extremely low surface brightness, but still that it had some non-rotational motions in some parts and where we had to apply our procedure. So this is our velocity field rotation curve coming from our velocity field that is much more stable to a larger radii than ones that we get from moment 1 and H3 velocity field. So the first part of our task was deriving these rotation curves. This is an example of one rotation curve. And how do we do that? By fitting this expression. It's a little bit more complicated, but this is basically it. Fitting this expression to an observed velocity field or derived velocity field. So it's not just fitting at one go, but it's done iteratively. We need to constrain because there is a lot of free parameters in this fitting procedure, we had to constrain center, systemic velocity, and these geometrical parameters subsequently, and to get the good grasp on our rotation velocity. And especially important are these geometrical parameters, and for them we did not set them fixed. We did not fix them to one value. We fixed them, but to a series of values. So we let them vary a little bit over the size of a galaxy disk, H1 disk, because but not just to have a better looking rotation curve or something, but there is a physical justification, like a vor present or something, or non-circular motion that would allow for this kind of variation. So at the end of this procedure, we were left with a number of these rotation curves that are describing the mass or total dynamical mass enclosed in a series of radii. And now we need to add more ingredients to our model. We said stellar, gases, and dark matter ingredients. Stellar came from Spitzer 3.6 near infrared micron band, and it is because it traces the massive old populations very well, and it suffers from least extinction, both internally and externally. And when we have like the surface brightness of a galaxy derived, we should still scale it with a really important factor, mass to light ratio, which is basically a main focus of our work. So this factor, we did two sets of models. First set of models is done with this parameter kept free, and the other one is with this parameter kept fixed, coming from stellar population models. So this is what it looks like when we see a one-dimensional representation of our fits that are actually two-dimensional of the observed surface brightness from Spitzer. So this is a small galaxy that we decided to describe only with an exponential disk. And this is the large galaxy that I presented before that is fitted, that its stellar component is best explained with exponential disk and bulge. So this stellar component, like what I said, this needs to be scaled with mass to light factor. What are we adding next? Gas mass. Gas mass is again coming from things observations. This is the zeroth moment of observation, which is an integrated intensity, but it is scaled to include other species of neutral gas, especially neutral helium, but and molecular gas was omitted at this point, although it can be contributed, it can be accounted for, but it is thought that it does not contribute that much to the total mass. And dark matter is represented with this very traditional isothermal sphere models and of our Frank-White models. All these components, stellar, gas, and halo, should add up to the observed circular velocity. So motions under the mass of the gas and the stellar component, the halo, are contributing to the total rotational velocity in this manner. Dust is also one of the things that you can incorporate in this analysis, and it's actually possible for this sample to derive a dust map but it was not. It is one of our future prospects to incorporate this, and we have this nice result from the mentioned papers that it says that it counts to from 10 to 30% to the 3.6 micron flux. So here is
5 minutes.
the result. Here is the main result. This is the main result, like dynamical modeling of a big spiral galaxy. So this is the observations, the black dots that we got before, and red is the model. So in this model, gas was fixed and free parameters were mass to light ratio of a disk component and mass to light ratio of a bulge component, and also the parameters of dark matter model. This is the same for Navarro, Frank, and White. So what does this gives us at the end? Masses of all individual components and how do they change over the course of this radii over the course of a galaxy disk. This is the same for the smaller galaxy that is only that only has one stellar component disk. And very briefly, what I wanted to say, like this other set of models with fixed mass to light use stellar population synthesis models that are based on works of Bell and de Jong and Into and Portinari that incorporated a huge variety of models based on a few different initial mass functions and combined with a lot of colors to get this histogram is only for one galaxy, NGC 5055, and for that we get a median value of, or most probable value from these models of that compares pretty well, I would say, to this free values that we got before. And it also is consistent best with this group by initial mass function and disk model. So for this second set of models, we also get a bunch of masses for all different components. And what is our goal here? To construct something like this. This is some distribution functions of masses in our immediate environment. And the goal is to compare it to the global mass functions, especially to the baryonic mass function. That's why we're so interested in mass to light ratio, because that determines the mass of baryons and how it compares to high redshift systems and to total. So here we see gas mass function, baryonic mass function, dark matter halo mass function, and baryonic fraction. Thank you all. These are some of my associates.
Thank you, Milana. It was a really nice talk, a very interesting presentation. So if there are some questions, please, we have time for that. Just unmute yourself and ask.
Hello, I will have a question. Michal Bilek here. Milana, it was a very interesting talk. It was also nice to hear you after a long time. I could have a lot of questions, but just one for the moment. The parameters of the dark matter halos that you derived, do they agree with the scaling relations? I mean the relations between the stellar mass of the galaxy and the dark halo mass, and the relation between the of the dark halo mass and the dark halo scale radius?
They agree pretty well with what we know about these dark matter parameters for now, but there are of course some few outliers, and Navarro Frank White model is as usual unable to fit very well some of this dwarf smaller galaxies. but still the parameters are within expected limits. Or
okay.
Okay.
Are there some more questions? If not, I can ask also one question. With the observations, what do you use as you use stellar population synthesis? Is this a 3D observations or just, I mean, how do you construct your curves?
I do not do, if you think that if we do our own spectral energy distribution fitting or something,
Yes.
we do not. We are using the models that describe that give us good correlations between the observed colors and metallicities and what should come out at the other end as in regards to this mass to light ratio. So we do not use observations in this part of the procedure, and they're based, these stellar population models that we use are based on some synthetical spectral libraries, and we plan to include some empirical spectral library that is very new and focused especially on the infrared colors that would be very useful for this kind of analysis, because we are mainly interested in the mass to light in the 3.6 micron band.
Okay, thank you. So if there are no any, are there some more questions or?
Okay, I can ask another question. How do you deal with the disk halo degeneracy? I saw that you have some fits where the mass to light ratio is a free parameter, and such fitting is known to be like sensitive to this disk halo degeneracy.
We do not deal with it at the moment. Yeah, we just what I said, left the parameters free for now, and look at this like contours of confidentiality to find some that are maybe in better agreement with current state of the art when it comes to dark matter parameters.
Okay.
I can explain.
So people usually include okay, I will write it.
Because we are a bit out of time, we already left. You can continue on a chat if you like with the direct questions, and we have to proceed with the next presentation. Daniela Kirillova, SFC baryogenesis model, inflationary scenarios, and reheating in the universe.
Do you see?
Yes.
Okay. So, hello. Thank you for the invitation to present my talk. I will, sorry. Okay, I will talk about a specific model of baryogenesis and our results of calculation of the baryon symmetry in this model in different inflationary scenarios and different reheating mechanisms. These are results on which we worked with my former PhD student, Mariana Poniatova, and now colleague in the Institute of Astronomy in Sofia. So first I will say several words about the baryogenesis model
a short description, this type of baryogenesis model. Then I will talk about the models of inflation and reheating, which we have chosen to use for our numerical analysis. And finally, I will present the results of the baryon asymmetry generated in this model for different inflationary and reheating scenarios. We all know that there exists baryon asymmetry of the universe, and its value is well measured now. The most sensitive baryometers being the Big Bang nucleosynthesis with the deuterium measurements being the most sensitive one for that. And the CMB anisotropy measurements also provide with a very good accuracy the value of the eta baryon to photon ratio, which actually presents the baryon asymmetry of the universe. And locally, up to 20 megaparsecs, we know that the universe is made only of matter. So antimatter is in insignificant quantities. However, how and when this net baryon number is generated, we don't know. There exists many baryogenesis models, among which the most often used is SUSY baryogenesis, baryon through leptogenesis, Affleck-Dine baryogenesis, etc. This type of baryogenesis happened at different epochs. So today we don't know exactly when the baryogenesis proceeded. The only thing which we know that it should be after the inflationary period and before BBN. So everything is possible. And the type of scalar field condensate baryogenesis I'm going to discuss is one of the baryogenesises which proceed starting from inflation, and the actual production of baryon asymmetry is around TeV. So it's late energy baryogenesis, kind of late energy baryogenesis. First ideas about this baryogenesis model and its analytical construction was made in our papers in 1989, 1990, when we were interested about the possibility of low temperature baryogenesis with Dolgov, which was my supervisor at the time. Then I worked with Chizhov concerning the applicability of this type of baryogenesis for expanding the large scale structure of the universe, especially the quasi-periodicity at large scales. And with Mariana, we were interested in the numerical account of particle creation processes for this type of baryogenesis, because as early as the 1990s, it was realized that particle creation played an essential role for baryogenesis and reheating. So this kind of model, in short, the baryon excess is generated at the inflationary stage and contained in a condensate of a scalar field, which is present together with the inflanton at the early stage, at inflationary stage. Then there is a specific potential for this scalar field, which at high values of the field amplitudes include these baryon violating terms. And at later epochs, at the so-called baryon conservation stage, the baryon charge contained in the field is transferred to that of quarks. So actually, the baryon asymmetry of the universe is produced. It can be, of course, further diluted or not. What we did is we followed numerically the evolution of the field and the baryon charge contained in it. This is the equation of motion, usual equation in motion, which includes also the this term of which accounts for the particle decays. The numerical analysis was done for a large range of parameters. These are described here for parameters of the model: the self-coupling constant alpha, the parameter of Hubble at the inflationary stage, and the mass of this field. We performed around 100 sets of parameters, 100 runs of the this numerical analysis And the problem was that we followed the evolution from the inflationary period till the BC epoch, which is a very long period. So sometimes these runs were for about a week or two. This was a problem. That's why it took lots of time. We accounted for particle creation processes. The idea that it is important first was proposed analytically in our earlier papers. Now with Mariana, we managed to first to compare the analytical and numerical approach for the account of the particle creation. And we found that there is a big difference. And in case we exactly numerically account for the particle creation in this model, there may be a reduction up to 2 orders of magnitude difference for the baryon charge. So it's important to work exactly numerically. Here you see the blue curves and the red curves for the correspondingly analytical and numerical account of the baryon charge evolution, of the, account for the particle creation in the evolution of the baryon charge. Okay, so there are different models of inflation and reheating. We know that the baryon asymmetry depends both on this baryon excess contained in the field, on the heating temperature, and also on the Hubble parameter and inflation. And there are many numerous models of inflation, hundreds of models of inflation. So we had to choose some of them just for illustration to see how the model works in them. Also, there are different scenarios of reheating processes. We considered the production of the observed baryon asymmetry in this model for these different possibilities for heating temperatures in different inflationary models. Our preliminary results were presented in our paper last year, which appeared in our conference proceedings. Now we are preparing a paper for a journal on the results which I'm showing here. The models of inflation which we used were the new inflation, chaotic inflation in supergravity, Chaffee-Wellington chaotic inflation, Stravinsky inflation model, and quintessential inflation. Of course, modern versions, not the ones which I have pointed here, of the original papers, where they were first considered. For reheating the process, I would like to say several words. First, reheating was considered perturbatively, calculating perturbative decay of the inflanton. And it was considered that reheating proceeded instantaneously, which means that the inflanton energy was converted very quickly, rapidly, to the, at the end of inflation, to radiation. And it was assumed that efficient thermalization takes place. With all that assumption, this is the expression for the temperature of reheating. It can be estimated, and using only perturbative decay of the inflaton, the temperature of reheating is quite low. It is less than 10 to the 9th GeV. Later, it was realized that actually non-perturbative decay of the inflaton into bosons due to broad resonance is possible. And this epoch is called preheating. Actually, it is the first thing which happens after inflation. And temperatures of reheating possible in that case are around 10 to the 12th GeV, also higher or lower, depending on the fact that which kind of thermalization is used, efficient thermalization or delayed thermalization, which is also possible. And in that case, smaller temperatures of reheating should be expected. More recent papers considering the type of thermalization can be found in these works of Mogaham and Mazumdar-Zaldivar. In short, from other point of view, there are other constraints on the temperature of reheating. It should be, of course, higher than the BBN epoch. So it should be higher than approximately 10 MeV and lower than 10 to the 11th GeV. If you consider Susi models and if you consider the possibility of gravitino production. So there are such constraints. Of course, there are also constraints from CMB data, etc., etc. That's why we explored several models of inflation and several possibilities for reheating temperatures in these models. The successful ones, from the point of view of our baryogenesis model, are presented here in this table. As you see, inflation, in case of efficient thermalization, presents possibility of production of baryon symmetry very close to the observational value, 7.10 to the minus 10. For the specified here in the second column, I specify the value of the Hubble parameter, the inflationary stage, and the heating temperature, which was used in our calculations. So the third column, fourth and fifth column show the parameters of the model for which the possibility of the baryon symmetry production of the order of the observational one is possible. So quintessential inflation also for these parameters of the Hashi and heating temperature, and three sets of parameters of our model is possible. In chaotic inflation in SUGRA, in supergravity, we have found several possibilities for temperature of heating between 10 to the 9th and Hashi 10 to the 11th and 10 to the 12th. There are four plots which of parameters which we found successful. And and for Schofield-Vilenki chaotic inflation, only in case of delayed thermalization, because for efficient thermalization, the baryon symmetry produced is not of the order of the observed one. So for the delayed thermalization, and this so in short, in summary, we have several successful models from point of view of this baryogenesis model. This is a type of chaotic inflation, modified Cherubinski inflation, chaotic inflation in SUGRA, and quintessential inflation, while new inflation, the old chaotic inflation model, a simple Schofield-Vilenki model, and also minimal supersymmetry model, inflationary model, the produced baryon symmetry there is several orders of magnitude bigger than the observational one. So the model is not working successfully for that inflationary models. In conclusion, we discussed scalar field baryogenesis model and its capability to produce the observed baryon symmetry of the universe for different inflationary scenarios. And I would repeat that the successful baryogenesis is possible for the modified Cherubinski inflation, Schofield-Vilenki chaotic inflationary scenario, chaotic inflation in SUGRA, and quintessential inflation. That is our finding of the several tens of models of inflation which we have discussed. It is noticeable that both Cherubinski inflationary scenario and quintessential inflation is also among the preferred scenarios today by the latest Planck's INBI data constraints. Thank you for the attention.
Thank you, Daniela. We missed your last slide. You can just share your conclusions, please.
Conclusions, okay. Here there are.
Okay, during this, thank you, Daniela, for a beautiful talk. And if there are some questions, now the panel is open. So if
Daniela, can you share your presentation, the last slide, please? Because we have some comments from
this one. Do you need this one, baryon symmetry, or the table?
The last. You can just open your presentation and go down to the conclusions and share the screen, please.
Oh, I thought it's the sheet.
We have.
There it is. Do you see it?
No.
Oh.
Just click green button, share screen. Just can you stop the presentation?
Okay. I'll try it now.
Okay, I don't think that this is.
Do you see it now?
Yes, thank you.
So do you need the last but one, or only the conclusions?
It is fine, thank you.
Okay, now the panel is open for questions. If there are any questions, please ask. If there are no questions, because we lost a lot of time now, we can proceed with the next speaker. Thank you, Daniela. And now Anna Mitrashinovic, various effects of galaxy flybys, dependence on impact parameters. As I can see, you don't have a limit until whatever you like to speak to.
Okay, give me a second. Okay.
It's 20 minutes talk.
Okay. First, let me just apologize for not including Faculty of Mathematics in my affiliations on abstract, since I'm a PhD student there, and this talk is based on my thesis, and I'll try to outline the main results briefly. So let me start with definitions. What we consider a flyby is an interaction where two independent halos interpenetrate but detach at later time and do not result in merging. And what I need to point here is that shouldn't be mixed with something that is also considered flyby, but it's more of a close approach where halos never actually overlap. And based on cosmological simulations, these interactions, these flybys as we define them here, are found to be as frequent as mergers on high and low redshifts for halo masses above 10 to 11 of solar masses. And of course, they're still frequent in intermediate range, but obviously not as mergers. And in some particular cases, when for some halo masses or some environments, they can even surpass the number of mergers. So what's the typical flyby? Typical flyby, intruder galaxy penetrates deeper than a half-mass radius of the primary, with initial velocity of 1.6 of virial velocity of the primary, and mass ratios of 0.1 or 10 to 1 on high redshifts and slightly lower on lower redshifts. So what do we know so far about these interactions is that based on previous research, these interactions can help and drive formation of warped disks, both visible in stellar components as well as gas. And they can also drive bar formation or even enhance the previous bar instabilities. And for various different initial conditions, they can also drive formation of both bars and spiral structures, especially two-armed spirals. And it was shown to be that these interactions, even weaker ones, can induce those features. So even weaker interactions than previously thought. And there's some current ongoing research on how do these interactions affect bulges of galaxies, especially how do they affect reshaping of bulges into boxy or disky. And it was discussed as a possible channel of formation of ultra diffuse galaxies, but more research needs to be done on that. So our motivation here is to further explore the dependence on impact parameter for these effects, and to see what role do they play in regards to all of these effects, and maybe possibly find some relation which connects a strength of these effects with impact parameters. And the way to do that, we ran a series of simulations with primary galaxy with real radius of almost 200 kiloparsecs and total mass of around 10 to 12 solar masses. And primary galaxy is modeled to be somewhat Milky Way-like. So it has three components: NFW dark matter halo, exponential stellar disk, and Sérsico bulge. And for the sake of simplicity, intruder galaxy is scaled to be 10 times smaller, both in mass and the number of particles. And this particular resolution on both primary and intruder galaxy is quite modest, actually, but it was kind of dictated by our limited resources. Interaction simulations were evolved for 5 billion years, and initial conditions are set to initial distance of 300 kiloparsecs, so almost contact system, with initial velocity of 500 kilometers per second, which is slightly larger than the most typical one, but it still falls into the some expected range of common velocities. And different impact parameters were achieved, but with same interaction duration. And we achieved that by varying, slightly varying initial position angles and velocity vector, but keeping the relative velocity constant. So a list of our simulation is given in this table. And where pericenter distance is actually impact parameter, I'm using these terms interchangeably. Impact parameters are listed in second column, and obviously our initial and rough estimate of impact parameters, and well, quite casual, slightly differs from the actual impact parameters. And it covers impact parameters cover a range of between slightly over 0.1 virial radius of the primary galaxy, but go slightly above half mass radius of the primary, since half mass radius of the primary is around 50 kiloparsecs, so it's in between the last two simulations. So what did we find? As for primary galaxy and disk features, we explored them using Fourier second mode, because it's quite a common procedure, which gives insights into bars and specifically two-armed spirals. And even though some more detailed analysis is needed, these evolution maps can actually tell us, even on first inspection, what is going on there. And spirals are manifested on these maps as regions of high enough amplitude and uniformly changing phase across disk radius. And bars are regions of high enough amplitude and almost constant phase. And first map shows our primary galaxy in isolation. So we can see that primary galaxy forms a bar later on, quite weak, but still forms it, and it grows until the end of simulation. So we need to take that into account. Spiral arms actually show really nice dependence on input parameters, since in close approach, their radii of origin is lower, so they start almost at the center. So they're almost, the spiral arms are almost nuclear in the closest approach. And as we go towards lower impact parameters, radii of origin shifts towards outer parts of the disk. So in a way, it's directly proportional to impact parameters, but however, their lifetimes are inversely proportional, since these strong and almost nuclear spiral arms tend to wind up and dissolve faster. And in simulations with higher impact parameters, some remnants of spiral structures or spiral arcs are still present in outer parts of the disk. So even though there is some nice relationship between strength and lifetimes of spiral arms with impact parameters, the picture is not really that great when it comes to bars, since it doesn't show any uniform dependence on impact parameter. Closest approach forms the bar rather quickly, and bar continues to grow until the end of simulation, reaching higher than 2 disk scale lengths in its length. And as we go towards higher impact parameters, in some simulation, bar evolution, even though it's bar forms, bar evolution is quite chaotic in its length. And this particular simulation is quite interesting because even though there are moments where the bar should form and there is some instability, it never fully forms and evolves. So the bar formation is constantly suppressed. Even the pre-existing bar in isolation. So the question is, should we here consider possible coevolution of bars and spirals, or maybe consider other effects which we neglected that might contribute to this? When it comes to intruder galaxy, it's much more straightforward. Stellar component retains all of its mass and doesn't undergo much of changes. But dark matter halo, however, gets stripped. And in order to measure the mass and determine mass of dark matter halo, we used 3 estimates. One, bound mass, is based on filtering particles with negative total energies, so gravitationally bound. Virial mass filters particles inside virial radius, which is estimated by fitting an FW profile to dark matter halospherical density profile. And core mass, as we define it here, is actually a quite common procedure in exploring dwarf galaxies, especially tidally perturbed ones in simulations, since it's based on filtering particles inside radius where circular velocity curve reaches maximum. So it's well-defined, very easy to calculate, and it actually contains majority of the mass. So it's a nice estimate to follow evolution of the mass. So as we can see, in all simulations, bound mass continues to drop until the end of simulation. That is mostly because bound mass also includes tidal features and particles that are still considered to be bound to intruder galaxy, which later on can detach. But some of them, like a minority of them, get recaptured, and that is seen in slight increase in virial mass. And virial mass fairly stabilizes longer after the encounter, since encounter ends slightly after 1 billion years.
Anna, just 5 minutes more.
Okay. So it needs some time to stabilize. And as for core mass, even though it kind of varies afterwards, it stabilizes almost before the end of the interaction. So in order to and virial and core mass fractions long after the encounter are kind of comparable. So we'll use averaged virial mass after it stabilizes to try to find some dependence on impact parameter. And on this plot, it's actually shown not as fraction, but as percentage of initial mass. And as we can see, it follows logarithmic growth really nicely. And same applies to dark matter to dark to stellar mass ratio, since stellar component doesn't lose any mass. Fit parameters are excluded here because they're most likely sensitive to initial conditions, mostly mass ratio in interaction, initial velocity, duration of the encounter, and so on. I mentioned that stellar component doesn't change much, but there is slight change in stellar half mass radius, although it's not as significant, since in the most extreme case, it increases by less than 1 kiloparsec. So, and to summarize, we found that intruder experiences significant dark matter mass loss, and consequentially decrease of dark to stellar mass ratio, and that stellar component remains unaffected, and that it shows logarithmic growth with impact parameter. And the question is that logarithmic growth universal with different parameters for different initial conditions? And the second more important question is, could stronger than these flybys or even subsequent ones strip intruder galaxy of majority of its dark matter, resulting in possibly dark matter deficient galaxy? And as for disk features, we saw that radii of spiral arms origin are directly and their lifetimes inversely proportional to impact parameters, but bars have non-uniform dependence, and bar formation can even be suppressed in some cases. So should we consider some interaction and coevolution of bars and spiral arms, or should we just explore other possibilities? So thank you. That would be it.
Okay, thank you, Anna, for the interesting talk. If there are some questions, please unmute yourself and ask. Now panel is open.
Hello, here is Michal Bilek again.
Hello.
And yes, so it was a very interesting talk about an attractive topic, at least for me. But I wanted to ask if you have investigated what is the effect of the loss of the dark matter from the intruder galaxy on the dynamics of the stars of the intruder. For example, if you remove this dark matter, if you expect some observable changes in the rotation curve or velocity dispersion of this smaller galaxy, and this could be compared, for example, to this could be a prediction for velocity dispersion of galaxies in groups or clusters.
Yeah, we did some analysis on that, but the results were, well, honestly quite boring since the stellar component didn't change much. So we actually explored global kinematics of well, the whole component, and even though it changes in most extreme cases, it's almost insignificant. I mean, it can be possibly fitted, but there was nothing
Yes.
well, attractive.
Yes, I think that even this finding is very interesting, and well, for me it's interesting because this is different from what we expect with MOND, with modified Newtonian dynamics, because here you expect that if you have a small galaxy close to a bigger galaxy, then its gravitational field would be weaker than if it would be in isolation. So here, what you are saying is actually an observable prediction that could allow distinguishing dark matter from this MOND modified gravity. So if you have this, then it is definitely worth publishing, I want to say.
Thank you.
Okay, are there some more questions? If not, we can conclude this session and thank all the participants and everybody who were listening. And if there are some information from organizers, please, Angelika, it would be nice if you can say what is the expected.
Hi, Eddie.